Hey guys, this is Lab 5, choose your own adventure. And so I chose to investigate the projectile motion of a styrofoam ball. The main problem was to use a computer model to predict the motion of a ball which is thrown upward and which falls down after some time, and to compare it with observational data. The results were that using Newton's second law and the momentum principle, the computer model was a good fit for the prediction of the motion of the ball, and it could be used for the motion future of the ball. So the main model that was used for this lab was Newton's second law of motion, which, as we know, states that the final velocity of an object is equal to the initial velocity plus the net force on the object divided by the mass of the object times delta t. So we know that for this lab of projectile motion, the final velocity is not equal to the initial velocity. This is because the ball does not have constant velocity. The graph is not a straight line. From this we can conclude that the net force on the object is not equal to 0. So we know that since net force is not equal to 0, the force that is acting on the object is the weight force, which we can define as negative mg hat, where m is the mass of the ball, g is the gravitational constant on Earth, which is 9.8 meters per second squared, and j hat is the unit vector pointing in the y direction. And since we made this a negative value, j hat is pointing in the negative y direction. Now let's go back and see the graph in the previous slide. We see that the motion of the ball is not linear, and we know that since the ball is initially thrown upward, the force of gravity will act downwards on it, will slow it down, and then eventually the ball will come to a rest, and then it will fall back down. Here is the main while loop used to create the computer model for this type of motion. We set t in the while loop to be less than 0.917 seconds because this was the time of our last observation. We defined the weight force as negative mass of the ball times g times j hat, which we defined earlier. We set the net force equals to W plus Fd, and Fd is the drag force, which we define as negative b times magnitude of the ball's velocity times the ball's velocity. This is a form of drag known as turbulent drag, which is a good way to model the ball in our lab. Then we set the ball velocity equals to the previous ball velocity plus the F net divided by the mass times delta t. This is essentially Newton's second law, and it calculates the velocity of the ball at each delta t, which we defined earlier. Or the delta t is 0.001 seconds, which is very small so that we can get accurate predictions. G is 9.8 meters per second squared. J hat is the vector 0, 1, 0 because we are only concerned about the y direction, and b, which we need for the drag force, which was part of the drag force expression in the previous slide. We find that by plugging in different values for b until we find that the final model value is equal to the final observation value. So here we get b to be equal to 0.045. Now let's run the model to see what it looks like. We see that the ball is moving up, and after a while it comes back down. This is the type of motion that we would expect. Here the graph shows the motion of the ball in the y direction. Now let's compare our observational data with our computation or the model data. The model data, which is represented by the red solid line, fits quite well with the experimental data, which is represented by the blue dots. the two fit especially well together at the beginning and at the end. This is because in the beginning we found the initial velocity of the ball by taking the first few points of the ball. And at the end, we found the b value in the expression for the drag force by setting the final two values of both the model data and the experimental data equal to each other. So we would expect the two to fit well together at the end. Now towards the middle and after, we see that there is a slight discrepancy between the two models. The model data slightly overpredicts the experimental data, and this could be due to the fact that we did not account for the shape or size of our ball in the calculation of the drag force. We also did not account for any errors made in tracking the position of the ball in tracker. Now, we see that from observing this graph that the ball reaches the 0 position at 0.8 seconds. This would mean that it would reach the maximum height at half of that time, or 0.4 seconds, which is about what we see here. Now, if we had thrown the ball with a slightly higher initial velocity, then the ball would remain in the air longer. It would take longer to reach its maximum height before it started falling back down again. And then the opposite would be true if we had thrown it with a smaller velocity. It would reach the maximum height a lot faster. Now, for this model, the ball will eventually reach turbulent velocity, or terminal velocity. This is because the drag force and the weight force will eventually be equal to each other, and the ball will be moving at a constant velocity.